Today, I'm going to cover acid and base equilibrium, and this will be the final part for chapter exam 14 and 15. Again, chapter 18 is a split between multiple chapters. Okay, we covered a little bit of this in chapter 13, and I'm going to also cover that in the 14, 15. Okay, so first of all, the review of chemical equilibrium. Let's go over the chemical equilibrium from last chapter. When the rate of the forward reaction equals the rate of the reverse reaction, and the concentration of product and reactant remains unchanged. This is when the chemical equilibrium is reached. For example, you have H2 plus I2, and then this is going to be creating HI, but at the same time, some of the H produced the HI is going to go back to the H2 and I2. And if that's the case, the equilibrium expression is going to be HI square because the coefficient is now going to become the power, and then the product over the reactant, and the reactant are H2, I2. Remember, this bracket represents the concentration measured in molarity. Okay, acid, base, and equilibrium. Acid and base dissociate in water. So here's an example of a general expression for the acid dissociation. So HA is basically the acid. So it could be anything: hydrochloric acid, hydrobromic acid, sulfuric acid, whatever. And then when we mix that into the water, what happens is that the hydrogen from the acid will dissociate and will be attached to the water to create the hydronium ion. And hydronium ion can be also considered just a hydrogen ion. They're basically the same thing. And they can be used interchangeably. And then now the A, which is an anion, right, doesn't have a hydrogen anymore because the hydrogen got detached. And equilibrium expression is going to then now look like this. Concentration of hydrogen multiplied by concentration of ion over the concentration of the acid. And again, we do not include the water here because this is not liquid, and the liquid is not liquid or solid, does not show up on the equilibrium expression. This can be also written as, again, we can just go ahead and take out the water out of the equation. Then that's going to look like this. And equilibrium expressions also can be written like that. Okay, for example, let's say that you have a nitrous acid that's going to put into the water, and then this is going to generate the hydronium ion and nitrite anion. Then equilibrium expression is going to be concentration of hydronium and the nitrite ion over nitrous acid. And for the acid equilibrium constant, we are going to be using a Ka. So we are going to be adding an A as a subscript, a subscript to express that the equilibrium constant is about the acid. And here's another version for the base. You have nitrogen trihydride that will react with water, and that's going to now generate ammonium anion, the cation, and also we have hydroxide anion. Then equilibrium constant for the base is going to look like this, and we're going to be using Kb, which is equilibrium constant for the base. Okay, strong acid and base. Strong acid and base completely dissociate in water. So we already went over this picture, so let me briefly remind you guys about this. So before the dissociation, okay, when hydrogen and anion got stuck together, but as soon as you put it into the water, all of them, essentially most of them are going to split into hydrogen and anion. So your equilibrium constant for the acid is going to look like this. You have H plus A minus over HA. So thus the concentration of HA is going to be nearly zero. Remember, after dissociation, you're going to have essentially almost nothing left for the HA because all of HA is going to split into H and A and keeping almost essentially none of the HA. Since the HA, the concentration of the regular acid form here, right, is going to be nearly zero because as this arrow is showing, this is complete one direction reaction. So the concentration of H and A will be much, much larger than HA. Therefore, the Ka value for strong acids are going to be typically large and much larger than 1. 1 is accomplished when you have about the equal concentration of reactants and products. Okay, but then since your H and A is going to be much larger than HA combined together, so concentration of this H and A is much larger than when there used to be, right? And then Ka values to be much larger than 1. So here are some examples of Ka for the common strong acid. So Ka for the hydrobromic acid, which is one of the strong acid, is about a 1 trillion. 1 billion. And then Ka for the hydrochloric acid is 1.3 million, and Ka for the sulfuric acid is about a 1,000. All right, what about for the weak acid and bases? Weak acid and base barely dissociate in water. So as you saw this graph last time, when acid is put into the water, not a lot of those HAs gonna split into H and A. Okay, most of them will stay their original form, and only a little bit of them are going to dissociate, which will lead into since H and A separated are small compared to the H and A put together, right? You're going to have a very small numerator and have a very large denominator. This is going to lead your Ka to be, for the weak acid, to be typically very small and a much smaller than 1. So Ka for the common weak acids are hydrofluoric acid, which is 6.3 times 10 to the negative fourth power, and carbonic acid are 4.5 times 10 to the negative 7, and hydrocyanic acid is 6.2 times 10 to the negative 10th power. So I hope you guys can see that for weak acid, Ka value is very small. Practice problem. Calculate the equilibrium concentration of a hydrogen and pH given equilibrium concentration of this acid is going to be 0.20 molarity, and Ka is 1.3 times 10 to the negative fifth power. Okay, so here is the equation for this acid dissociation. So here is acid before the dissociation, HC3H5O2. This is called the propionic acid, by the way. And this is going to split into the hydrogen and propionate ion. Okay, and what's going to happen is that your equilibrium expression is going to look like this, where H will split, and then you have an anion over the acid. We know the concentration of the cation, hydrogen ion, and anion are the same because they split into 1-to-1 ratio. So whenever we break or dissociate the acid, we get an equal molarity of each one of them. And since they're 1-to-1 ratio, if I substitute one of them as an X, the other one is also X. So I'm going to put them X times X over the concentration of the acid. Now to solve for the X, because we need to first find out the concentration of hydrogen in order to calculate the pH level. So I'm going to go ahead and isolate the X by itself, and then once we have this equation set up, and you can plug in your numbers, and then using the calculator, you'll quickly find out the concentration of X, which is the hydrogen, right, is going to be 1.6 times 10 to the negative third power molarity. And then we're going to be using the concentration of hydrogen to calculate the pH level. So the pH level is negative log of concentration of hydrogen. Go ahead and plug in the number from the calculation, and then you find out the pH level is 2.8. Calculate the Ka for the solution with equilibrium concentration of 0.30 molarity, monoprotic weak acid, and pH is 3.65. Okay, so I'm gonna go ahead and first write out my skeleton equation that looks like this. The acid breaking it down into the hydrogen ion and anion. So the equilibrium expression should be the product over the reactant. And we know that the concentration of H and A again are 1 to 1 because their ratio is 1 to 1. So if I'm going to substitute one of them as X, the other one can be also expressed the X in terms of a molarity and concentration. Now, since we are given the pH this time, I'm going to have to go ahead and use the pH level to now go backward to calculate the hydrogen. So I'm going to go ahead and use this formula that we already know. The concentration of hydrogen is 10 to the negative pH power, which is 3.65, and I find out the concentration 2.24 times 10 to the negative fourth power. Now I'm going to go ahead and plug in this number into this formula again. And then again, the concentration of hydrogen should be also same as the concentration of anion. So multiply them together and divide by the concentration of HA, which was given to us, 3.0 molarity. And that will give us then Ka value.